So a few quick announcements on the screen. Probably just the biggest one. The only thing that's new is just like a few shifting of office hours. So I have my regular office hours today, 2 to 3 in person and Zoom. And then Friday, I'm adding an sort of an office hours from 1 to 1:45 that overlaps a little bit with Juz. And so we'll just be in the same room. And then no Wednesday office hours next week. That'll be right after the homework is due and sort of the project will be released right around then. So just we'll cancel Wednesday and then we'll add some extra ones to make it easy, like better for the project. Other than that, if you please sort of be in the final steps of finalizing your project partner, I'm going to release the details in the next week. And so it'd be good to hit the ground running a little bit. And there's a form on EdSTEM for if you need help finding a partner. Any questions on logistics? No, so no late days on the project. Yeah, yeah. Any other questions? Oops. Let's see. Clicker stopped working. Okay. So just as a reminder to pick up from where we left off on Monday. So last time we talked about, well, experiments with interference in general, but in particular, we talked about network experimentation. And we sort of had this two-stage approach that I just want like y'all to keep in mind. The first one is, so at the very beginning, you just get some graph, you get some fact for the world, and there's nothing you can do about it. And because of the sort of the interference relationships, you want to design an experiment to sort of minimize the interference or to measure the interference or sort of to make it such that like you can still get a good estimate out of your experiment. And then you get some outcome generation, and then we sort of do some analysis on, we have some outcomes on different clusters or different individuals, and then from that we want to get the global treatment effect. And in particular, last time on the design component, we talked about graph cluster randomization. So instead of randomizing each individual in your network, you sort of randomize clusters on the graph, where a cluster is approximately a bunch of people who have strong connections with each other, but have weak connections with everyone else. And we didn't really talk about analysis, and I'll say a few more words here later, but like in this class, we're not really going to focus on analysis. We're going to be focusing on the design component, because probably the most important thing about experimentation is getting the design right and recognizing bad designs. And so today we're going to talk about, I think, like 2 or 3 other designs of experiments that you might see in other settings. Any questions from last time? Okay. And so the other general lesson to keep into mind is always think about what the unit of randomization is. So so last time what we talked about is in a social network, if the unit of randomization is an individual, each individual you flip a coin and you do treatment or control, then that has interference between treatment and control. And what we talked about was we think about changing the unit of randomization from individuals to clusters. And that's going to be, in some sense, the general framework for the experiments today as well. Is we're going to think about, okay, so what unit of randomization is right for this setting? And what you care about in unit of randomization, what you care about is sort of, you want clusters to be close to independent of each other. And so in the social network setting, this meant that you want 2 clusters, if one's in treatment and one in control, you want very few friendship ties between the first cluster and the second cluster. Or you want few strong friendship ties, or however you define ties. And if that happens, if these clusters are actually independent, then your experiment is going to be unbiased. And I'll say a few more words about this later. And then the downside is that sort of your sample size goes down with the size of the cluster. right? So if you have bigger clusters, you can have fewer clusters, and that hurts your experiment power. And so there's this trade-off between making bigger clusters to try to get them to be independent and wanting small enough clusters so that you still have a good sample size. And that's going to be the trade-off to keep in mind for sort of everything we do today as well. Okay, so we kind of started on this with Hannah's guest lecture on Monday evening. If y'all didn't go to that live, or I guess remote live, then please watch the video. It's posted on Canvas. So today is going to be building on the guest lecture. I'll do a little bit of recap for those of you who weren't there. Okay. So in social networks, we had interference between treatment and control because of friendship ties, right? The whole point of a social network is that sort of activity is defined between individuals. And so how one individual feels about the platform or behaves on the platform is going to change how other people feel on the platform. And today we're going to sort of talk about how similar interference can arise in marketplaces, but not because of these friendship ties, but because of competition. Okay, yeah, so I just said this, okay. And so in markets, interference rises from competition and capacity constraints. And Hannah gave an example of that on Monday, and I'll repeat Monday evening, and then I'll repeat some of that today. Okay, so why does this happen? Like, so what's like a high-level example of competition? Suppose, and so this should remind you of the pricing lecture and pricing multiple items at the same time. So if I make half the products on my marketplace cheaper, right? So if I remove fees for half the products on Airbnb, customers are going to increase their purchase of the cheaper items. And why are they doing that? If y'all remember the pricing lecture, there's two effects. The first one is there's some customers who go from purchasing neither item, no items, to purchasing the new cheaper item, or like sort of the now cheaper item. And that's maybe the good kind of effect, is you just converted someone from not being a customer to being a customer. But then there's going to be other customers who move from the more expensive item to the now cheaper item. And that's called cannibalization, and that's maybe the bad kind of effect that you want. And it's bad in that it decreases your revenue, but it's also bad in that this creates now bias in the experiment, right? So why does this create bias in the experiment? Because this is not representative of what would happen if I make all the products cheaper. If I make all my products cheaper, then this cannibalization effect won't occur, because now sort of like the thing that you moved, the moving from the more expensive to the cheaper one doesn't happen because there's no more expensive item now, right? So not only is this cannibalization maybe bad for your revenue, this is biasing your experiments. And that's because your experiment world looks different from the global treatment world where everyone gets the treatment. Okay. Yep, and so today, so Hannah gave one example of an experimental design to maybe either mitigate some of this interference or at least be able to measure it, and then you can do some fancy analysis to fix it. And so today I'm going to give 3 or 4 other experimental designs that might work in markets under interference. Any questions so far? Okay. And so, okay, so what's the first approach? The first approach is just take the exact same idea from social networks, but now apply it to marketplaces, right? So the first approach is graph cluster randomization in marketplaces. And so what do we do? So this is actually the same example that Hannah gave on Monday from Airbnb. It's this paper from a few years ago from a few, I guess, then MIT researchers. I got these slides from Dave Holtz. He's a professor at UC Berkeley now. And he does a lot of really nice work on experimentation in marketplaces. Happy to send more links later. Okay, so in this paper, they describe this experiment that they ran on Airbnb, where what they wanted to know is what happens if I reduce listing fees. And what they found is if they do like a classic A/B test where they randomize at the level of the listing, then you'll end up lowering fees on about half the listings in this area. And they found that bookings for these listings went up 3%. And that's absolutely huge. Sort of very few experiments get that big of an effect size at like a place like as optimized as Airbnb already. Yeah, so if you lower the fees on half the listings, things went up 3%. But it turns out, sort of through their experimental design, they were also, they were doing some they were trying to evaluate different experimental designs. And then what they estimated was sort of if they instead had lowered the fees on all the listings, so sort of they had some other areas where they did just lower the fees on all the listings, then overall bookings were flat, right? So this is exactly what I just sort of the high level example I gave on the last slide, where reducing fees on half the things led to an effect, and then reducing fees on everything led to no more bookings. And so here they estimated that this was essentially purely cannibalization that was going on. Okay, so what are some various, okay, so what's the idea? The idea is that we want to use the things that we learned about graph cluster randomization and social networks and apply it to Airbnb or apply it to marketplaces in general. Now, what's the challenge? And so, okay, and so what do you need to do? You need to go from listings, which is some points in space, and to a graph of some kind, where two listings are connected if if they would interfere with each other, right? So that's the intuition that we want to get from social networks. And the challenge, and so the first challenge now is, okay, yeah, so you want to connect two listings if they would interfere with each other. And what's a reason that they would interfere is if two listings are substitutes, right? So if someone logs into the marketplace and instead of buying item A, they saw that item B was cheaper and they think that those two things are roughly equivalent, and so they went with item B instead, right? So you want to be able to connect, you want to be able to create a graph where two listings or two items are connected if they're if like the thought process I just went through would happen, if they're substitutes. And just I just want to point out here that this is now like an additional complication step to running graph cluster randomization. So like in a social network, you have it's not trivial in a social network, but so in a social network, at least you start out with a graph, right? At least people have told you who they're friends with and who they're not friends with. And okay, maybe friendship is not the right analog for interference, but you can also measure all sorts of things like this is how often this person talks with this other person and so on, right? So you sort of already have all the data you need to construct the actual graph that you want to do cluster randomization on in social networks. Here, you sort of have to use marketplace data to learn the network structure. And maybe in this setting, what they just and it's not just purely spatial geographic, right? It's there has to be some connection to the underlying map. So for example, in this setting, all these dark green houses are geographically, they're not super close to each other, right? This thing at the top is very far driving distance or crow's distance or whatever you want from this thing at the bottom. But they're all substitutes because they're all next to the lake. And then you have this clump here that's okay, not really, a few of these are on the lake, but I think this is the town of Tahoe. I'm not actually sure. Okay, great. Yeah, so this is the town of Tahoe. And then up here, you sort of have the skiing resorts, right? And so you need to be able to learn, you sort of need to be able to extract this from the data that people who sort of might be looking for this thing at the top would be competing or would also be looking for these houses at the bottom and not the things in the mountains. And to do this at scale is potentially non-trivial. And then here's sort of maybe another clustering thing that emerges in the South Bay in San Francisco or near San Francisco. Okay, so once you learn that network structure, then do exactly what we talked about last time. Just find cluster, like sort of each cluster assigned to either treatment or control, and then do the analysis. Now, the challenge with this, and I'll give a few examples very soon, is that the graph just may be way too interconnected. So for example, in Airbnb, you don't know if someone is, so like, yes, like these houses are competing against each other, but if I'm a consumer, wanting to book a place on Airbnb, I might, this could also be competing with like lake houses in some other state, right? I could just be looking at, I have some vacation days, I want to be in a house on a lake. There's no reason I need to be in Tahoe compared to some other house, right? And so interference might be fairly far, and like clusters that seemingly are far apart might actually be interrelated. And Hannah's lecture on Monday discussed this paper in a little bit more detail on like how they actually did the measurements that I talked about. Okay. And so, okay, so that's a challenge. In other networks, so like in ride hailing, you can also do cluster randomization, but in some sense it's easier in that you already have the clusters and that it's purely geographic, right? So this is from a blog post from Lyft. I think I linked it on the course website, and this is just showing that so the pink areas are their treatment areas, and their white areas are their control areas. So they had some product, I don't know what they were testing at this time, where they just took the city of Denver and just assigned different hash, sort of what are called geohashes, for those of you who worked a lot with geographic data. And so they just assigned different grids, squares on the grid overlaid on the map into either treatment or control, right? And then the idea, hopefully, is someone looking for a ride in this pink area is not interfering too much with someone looking for a ride in the white area. Yeah, okay, so the question is okay, so the random question is what's the difference between using hexagonal and squares? There's some weird technical differences. There's also some like cultural differences. So for example, Lyft uses squares, Uber uses hexagons. Yeah, happy to talk about that offline. Yeah, it's, yeah, okay. Okay, so so you can just randomize at, so instead of doing like actually learning this like fancy graph, in ride hailing maybe it's or like marketplaces that are purely spatial. So like maybe like dog walking marketplaces would also be something like this, like a dog walker doesn't want to travel too far. Yeah, so you can just do purely spatial randomization. And the reason I have this this up here is because we want to maybe start thinking about the level of granularity of the clusters, right? So both of these are the same Denver map, so it's the same level of zoom. It's not like this left map. Oops. It's not like this right map is like zoomed out. This is just the same level of zoom, but it's like now they randomize at a far finer scale. And so maybe they have a product where they think, okay, this like sort of, even if two things are half a mile apart, they're not interfere, like the treatment and control won't interfere with each other. And what's nice is that you get a lot more clusters in the same area in the finer grid than the coarser grid. Yeah, so the question is why spatial grids here as opposed to some like meaningful units in reality? Partially, so okay, so in like in a marketplace like ride hailing, um, spatial distance on the globe is a very sort of useful, like it is like fairly highly correlated with like reality interference metrics. Now you might think that there's like you actually want to do driving distance and not like spatial distance on the grid. But then as soon as you start thinking about driving distance, then it's like okay, but like maybe time of driving is like instead of like road network, and then that's like the time of day, and so you could sort of do it at that level where you and I'll give some examples, and sometimes you do, right? So like sometimes you'll do like this suburb versus that suburb, or this part of the city versus that part of the city. But that's an incredibly hard thing to do if you have a product with sort of like on this like right-hand side, for example, where like just like learning that interference structure at this fine granularity and then seeing how that depends over time and stuff is just, it's like a hard thing to do. And I don't know if there's good evidence that you can do it well. And so if you have this many clusters, then like maybe just do spatial geographic. If you have fewer clusters, maybe like really try to get them right. Yeah, so that's we're going to talk about exactly that in a sort of later on. Yeah. Okay. Yeah. So right now we're still talking about spatial or sort of like graph-based or spatial-based randomization, where each unit of space or each listing either gets treatment or control the entire time. And so in that sense, I just view this spatial randomization as a kind of graph cluster randomization. Yeah, and then you sort of do the same exact analysis that you would do in the other settings. Are there any questions about either graph cluster or spatial randomization before I move on to other kites? Yeah, so you just split up the world into grids. So these are, I think, geohash 5 and 6, maybe 6 or 7, some geohash number. And then for each geohash, you just flip a coin and decide treatment or control. So it would be in the sort of, yeah, so let's walk through an example where it would be. But like, for some products, it might not, right? So depending on the product that you're testing, it might not sort of like these large units might not interfere with each other. Depending on the product of testing, these might not interfere with each other, but of course they might. And so that's one of the big challenges of this approach is that sometimes it's hard to create these clusters where clusters don't interfere with each other. And it's oftentimes much harder in marketplaces than it is in on social networks. And so what's maybe the next thing you could try, and so is maybe try sort of what the question was on, is you have another unit to take care of, right? You can not only split up space, but you can also split up time. And so, and this is one of the dominant modes of experimentation in marketplaces today, is now you also think of time as another dimension to split up. And so before we get into maybe defining experimentation over time, so I think we've discussed many of these challenges already, right? So like, why would you maybe think space is not enough? It could be difficult to define the clusters. They're legitimately, and then maybe, the second one, and I'll walk through the example now, is there legitimately may not be enough clusters that don't interfere with each other. And so why, and yeah, so I've said this example where in Airbnb, rentals near Disneyland may compete with rentals near Disney World. And it's like learning that graph structure might be a little complicated. In ride hailing, it happens for, I think, a quite sort of a very different subtle reason, because it's a two-sided marketplace. And I want to walk through this example because you might see similar effects in a lot of other two-sided marketplaces. And so like recognizing things like this is, I think, pretty important. And so what happens there is a driver sort of interference is happening in marketplaces because of driver decisions. So it's not that like a one rider, like I'm in Roosevelt Island and I'm like choosing whether to go to Manhattan or choosing to go to Queens depending on the prices, right? That's probably not what's happening. Like Queens and Manhattan are not competing for where I'm going. I'm probably deciding where to go and then looking at Uber or Lyft. But drivers are deciding where to drive based on payments, right? They don't care where they, near the end of the day, they care where they end up. But like in the interior of the shift, in the middle of their driving day, they don't care where they are. They just want to maximize money. And so that causes interference. And so let's walk through an example. These slides are from created by someone at the Uber Marketplace Experimentation team. I wish I knew who, but I don't. Okay. So suppose the city has two geographies, just a downtown and a suburb. And, as you might expect, there's always fewer drivers in downtown compared to the people who need rides in downtown. And then there tends to be oversupply in the suburbs. I guess for the sake of this example, I don't know how true this is anymore. But so suppose there's an oversupply of drivers in the suburbs compared to the number of riders. And so the thing that they wanted to test out was, okay, can we find out a way to fix this supply-demand imbalance? And what they wanted to test was, what if I just tell drivers in the suburb to go to downtown? Like, I don't send surge signals, I don't like pay more, but I just like send them a little like notification on their phone to say, you'll probably make more money if you go to downtown. Right, so they just like provide tips to the drivers. And so, okay, so they want to test out, okay, does this thing actually work? And so what they did was they picked just in the, so their treatment units, they said, were 50%. So they didn't actually run this experiment because they knew this would go bad. So this is the counterfactual if they had run like a simple A/B test. So in a simple A/B test, or even in, this is like some weird mix of cluster randomization and a simple A/B test, where they said half the drivers in the suburbs get this new feature that says, okay, go to the city. And the other half of drivers in the suburbs don't get this new feature. And none of the drivers in downtown get a feature for like, okay, go to this part of downtown or go to this like really lucrative spot. So control is all the drivers in downtown and half the drivers in suburbs. And treatment is half the drivers in the suburbs. Okay, and suppose that some of these drivers actually listen to the notification and go to downtown. Then, and suppose that, and it's okay, so they did this, or suppose that they did this, and that the outcome is, in the treatment, these drivers are earning $40 per hour. But in control, they see, okay, these control drivers in the suburbs, let's forget about the control drivers in downtown. These control drivers in the suburbs are also earning $40 or 40 units per hour, or whatever that unit is. No claim that it's dollars. Okay, so they're also earning 40 units per hour. And so maybe one conclusion from this experiment is that the notification didn't work, right? That treatment and control earned exactly the same amount of money on average. And so maybe you shouldn't do a feature like this. And so on the basis of this test, you might conclude that this product does nothing. But my claim here is that sort of there was interference, there was contamination between treatment and control because you move drivers from one place to the other. And so suppose, and the claim on these slides, and my claim in this example, is if you had done nothing, if you had sent no one these notifications, that average earnings in downtown would be 40 or 45, whatever, units per hour. And earnings in the suburbs would be 30 units per hour. And so every driver in the suburbs who got either treatment or control would be earning 30 instead of 40. And so why is that reasonable? And so under this, what I'm thinking would have happened under global control. Why is that reasonable? Okay, so under what would have happened, the experiment actually raised earnings for both treatment and control drivers by $10, right? So launching this product to half the people, it doesn't matter which half, raised earnings for everyone in the suburb, whether they were in treatment or control. And so why is that reasonable? So what happened? Does anyone, I guess I've been talking a while and I need some coffee. Does anyone want to take a stab at what happened?
Removing half the drivers in the suburbs, then the supply of suburb drivers goes down. There's more of a that price goes up. Downtown, you already have a premium price for being downtown.
Yep, exactly. So I'll just repeat it is, so by giving the treatment to some drivers, you decrease competition in the suburb and you increase competition for drivers in downtown. And so both driver level A/B testing and graph cluster randomization, where the suburb was treatment and downtown was control, would lead to biased estimates. And to prevent such a thing, you'd have to cluster at the city level to prevent such interference. And maybe the second thing I want to point out with this example that I don't have on the slides is that this is, I think, a good example for how tricky it is to think about what happened under global treatment and global control, right? And so in this sense, it's like I'm not even sure what the global treatment is. So if I gave half the drivers notifications to go to downtown, then that decreases, competition a little bit in the suburbs and increases it a little bit in downtown. And so maybe I get these good effects. If I tell all the drivers to go from the suburb to downtown, then this would be magnified even more, right? Then we'd be like severely undersupplied in the suburb and potentially oversupplied in downtown. And so you might actually decrease earning, right? So like the drivers who didn't follow your notification might be the ones who benefit. And so it's not clear here that global treatment actually means telling everyone to send the notification. Global treatment might like legitimately be that you decide areas that you want to send drivers to, you decide areas that you want to send drivers from, and then you only send the notification to a few people in each area, right? So in this example, it doesn't even make sense to think about treatment applied to individuals. You really have to think about the treatment as something that's applied to areas. And so that happens, I think, in a lot of settings where like you could like there's like something you can do to an individual, but the treatment is like not what you're doing to the individual, it's what you're doing to this like class of things that are competing with each other. And that's because and this is what's called like equilibrium effects, is that really what Uber is trying to change is the equilibrium of how many drivers to riders there are. They're not trying to change what any individual driver is doing. And so because of that, if they apply treatments at the individual level, then you might overshoot the equilibrium that you want to create. Okay. And so in this example, you would have to cluster at the city level to prevent such interference, right? You would have to say the entire Bay Area is in treatment where I'm going to tell people to go from the South Bay to San Francisco, and entirety of like sort of the New York area is in control where I don't tell people to go from Staten Island to Manhattan. And then you would have to compare what happens in those. And something like that still might not be enough because, for example, drivers commute from Sacramento to San Francisco to drive often, and that's like a 2-hour drive. And so maybe even city level clusters wouldn't be enough for an experiment like this. Okay, and so what hopefully this has convinced you is that spatial randomization is hard and often not effective, right? And so certainly, so far we've thought about partitioning users across space or across like areas in this like abstract network that tends to be correlated with space. And this might lead to too much interference across space if there could just not be enough unique space clusters. And the idea for this next set of, or sort of this next experimental type I'm going to talk about is also partitioning over time, right? So allocate the same set of users, the same city, the same region of space, whatever, the same cluster on the social network, to treatment or control at different times of the day. And okay, so what's maybe the most naive thing that you could do? The most naive implementation of this is pretend right now is time 0, then up to time, and I think this is exactly what you suggested earlier on, is right now is time 0, up to some time t, allocate the entire city to control, and then from time t to 2t, allocate the entire city to treatment. And t can depend on whatever the thing that you're experimenting is, right? It can be hours, it can be days, it can be months, whatever. Do people have thoughts on why this might be a good or bad idea? Okay.
So let's say you run the experiment for a month during the summer, and then fall comes around. Obviously, that affects how the market results.
Yeah, exactly. So sort of what could be going on, or what does happen in a lot of these marketplaces, is that there's incredible seasonality. So I mean, certainly on the order of a year. So certainly like Airbnb over Christmas is different than Airbnb in August. And so there's like literal seasonality with like the seasons. But there's also, and I think I showed y'all some of these plots in like the ride-hailing pricing in the pricing lecture, is there's incredible sort of fluctuations in a lot of these markets, like not just over the year, but over like a month or over a week or even over a day, right? Or like within an hour, right? Is that there's just like an incredible amount of this fluctuation, and that might mess up your experiments. Okay. And so I think this is captured really nicely. So there's this blog post from 2014. So like what I would say early in the age of digital experimentations, or doing digital experimentation right, by someone who at the time was a data scientist at Airbnb, Jan Overgoor, but he's now, or I don't know his current status, but he was until recently at least until recently a PhD student at Stanford. And so what he says in this blog post is that often the outside world has a much larger effect on basically any metric that you care about than your experiment, right? So like the effect of your experiment is completely overwhelmed by just like the effect of your marketplace, and just like time and like everything else going on. And so he sort of gives this plot from Airbnb where this is some metric that they care about. And so on January 20th, they launched the product. And during this peak time, it was in treatment. And then on February 20th, they stopped. And now they want to know, okay, what was the effect of the product? And maybe the product had some difference, right? Maybe the product is slightly above the counterfactual line of where it would be of like, if you hadn't launched the product. But whatever that difference is, it's completely overwhelmed by, whatever this metric is, it tends to be increasing from January 1st through February 15th on Airbnb, right? And so if all I did was this naive time experiment of up to a certain time do treatment and then after that do control or vice versa, then like I just have no hope of calculating this difference effectively. Yeah. Any questions or thoughts here?
Netting out some sort of historical observations or structuring the experiments in a way that
Yeah, great question. So the question is effectively, could you like cancel out the seasonality in the analysis? Could you sort of use probably some machine learning model to be like, okay, so I know this metric tends to increase in from January to February 15th, and then I can just cancel out that seasonality. So build a model for what would have happened without my launch, and then compare to that. And for those of you, I don't know if any of you are like in like the financial engineering program here, sort of have taken classes that do like time series analysis. And like in theory, there's like good methods to do something like that. Sort of there's an entire class of machine learning models or like ARIMA models that can like detect seasonality at different levels and cancel things out. And so in theory, you can do something like that. And we're going to discuss a method that is, so later on, I'll introduce it at the end of this class, but I don't think I'll have time to get into it today. And so I'll start it out next class with this. But in theory, and so there is a method called synthetic control that like philosophically tries to do something like that, where it tries to build a model for what would have happened if that unit was in control and then compares against that model. Now, you don't exactly use like time series for like from previous seasonality trends, because it turns out in most marketplaces, sort of actually stepping back a bit, it's a little hard to distinguish between what people do because of like where people are running these experiments, right? So like it's a little hard to distinguish like our current things that I'm teaching and like trends because like these things are being used in like certain market, like primarily being developed by at online marketplaces that are still like super growing and changing every few months. And like if this was instead being developed in some other domain that like the world isn't changing, like people would do things like that. But like at least in marketplaces, and so the claim I'm going to make is at least in marketplaces, you can't just use last year's seasonality trends, right? Because these marketplaces are trying to at least grow 20% a year. And then sometimes COVID hits and right. So like doing that effectively is incredibly hard. And what synthetic control tries to do is use what's going on in the marketplace today in other places to develop a model for what would have happened. Okay, but yeah, so we'll get to that eventually. But then the other solution is sort of is an experimental design. So that's an analysis solution. What I want to cover today is an experimental design solution. Is how do we like design an experiment that might hope to get around something like this? Any questions here? Yeah. So the question is, if we choose our unit a day, then underlying changes would be less significant. And so I mean, yes and no. So um, if you do, if you do treatment for a full day and then control for a full day, then sort of what that prevents is like the hourly changes. So right, like so you capture rush hour in both treatment and control. You capture whatever like 3 a.m. in each unit treatment and control, but you might be susceptible to longer run changes, right? So what if my one day was Thursday night, my Thursday, and then the second day was Friday, right? So like a lot of these marketplaces behave incredibly differently on the weekends. And so I think I showed y'all the plot, like a plot earlier of like demand in Wright Austin over a few, like over on the order of weeks. And then you saw this spike every weekend. Okay. And so, but yeah, but that's exactly on the right track. And so the idea is, okay, so what can you do to like try to capture both of these things, where you sort of get diversity within sort of like you make sure that each treatment and control gets like observes like the full spectrum of like what the marketplace offers during the day, but then you're also not susceptible to maybe these longer run changes. And the idea is simple, is that instead of just doing control for some period of time and then treatment for some period of time, you just keep switching back and forth. And this is called a switchback experiment, where, and the way I'm going to present this and like the way it's done in reality is you can layer this on top of a spatial randomization approach. So for each region, and define a region as city, graph, cluster, center, whatever, simply switch back and forth on whether the region is assigned to treatment or control. And so this is from a blog post on DoorDash about these experiments. An aside is this experimentation module is like, in some sense, much easier to teach than the others because sort of all of this stuff is being developed today, like at these places, right? Like this is all, like a lot of this stuff is like new in the last like 5 or 10 years at a lot of these companies, or like turns out switchbacks are an idea that's like decades old and used for like I think cow lactation, but the modern mass usage of a lot of these experimentation techniques is like 5 years old. And so there's like an incredible amount of like nice blog posts written by data scientists and engineers at these companies on like how it's done today. There's a lot of active development, and there's a lot of active research from like whose slides I can steal. But I think sort of that being said is sort of the reason I'm pointing that out is sort of I sent like sort of I'm putting a lot of these links on the course website, and so if this is something you're more interested in, like sort of just like go and read all of this stuff and link follow from there. And there's like an incredible richness on like how people do experimentation and practice that's just available online. Yes, either of you. Yeah, so I'll describe the actual experiment in a second. Yeah, or yeah, and like things like that. Did you have?
Yeah, what are some of these new experimentation, or are these new experimentation methods like themselves experiments? Like, are these, do they start from a theory and then become a method, or are they more
Yeah, so that's a good question. So the question is like, the experiment is itself a product, right? There's some engineer whose like job is like running good experiments. And how do you know whether an experimentation is good and how an experimentation design is good? And so Hannah talked about some of that on Monday, or like she gave a glimpse of that on Monday, where she talked about two methods. The first one, so she also talked about that Airbnb paper, Dave Holtz, that like I like flash results from at the beginning. And what they did, and what she talked about, is they ran like an experiment within an experiment. So in their setting, they like had this intuition that cluster randomization is actually pretty good. And so they like sort of knew that like cluster randomization would give roughly unbiased results, or maybe it would be biased in one direction, but you know the direction, it's like, and it's not that bad. And then within that experiment, they ran like a simple A/B test, or like other types of experiments. And then they calculated sort of the difference between treatment and control, right? Or sorry, like they calculated the difference between the measurement in each, like sort of this like internal experiment and like the meta experiment that they knew was pretty good. I'll talk about this briefly next time. Is you can also, and there's a Lyft blog post about this that I posted, which you can also use simulation. So what they did is, so Lyft has, and like a lot of these marketplaces have really high fidelity simulators internally for like how their marketplace behaves. And so they have this like cute little thing where like they simulate like customer demands with various models. They simulate driver behavior. They simulate, you know, the physics of like driving and matching and all of that stuff. And anything, and so what this experiment or this blog post talks about is anything that they can, and what's nice is that the simulator takes essentially the same code base as their like real product. And so anything that they want to launch real, they can launch in the simulator first with the same code, see how it does. And then if it performs well there, then they can run an A/B test. So that's like step 0 to running an experiment. And then run the experiment. And if it does well in the real world, then they can launch. And what's nice about simulators is you can also use this to like evaluate different experimentation techniques, right? So in simulators, you can program the ground truth. You can program that like this is the effect size. And then you can see how do different experimentation techniques, like how close do they get? And then that relates to maybe the third method that Hannah talked about on Monday, which you can also use I mean, in practice you'd use simulators, but like in theory in academia you could also use like theoretical models to like model the world and then prove things about how the world behaves under that model. Okay. Any other questions? That was a fairly long aside. I'm happy to do more of that. I think I have time. Okay. So back to switchbacks. So what's the idea? For each region of space, just switch back and forth between whether that region is assigned to treatment or control. Okay, maybe not exactly back and forth. So as you'll see here, you know, sometimes the same region is assigned to treatment twice in a row. Sometimes it's assigned to control twice in a row. It could happen that it's assigned to treatment 3 times in a row or something. But so in reality, what you want to do for like a subtle reason is every unit. So now every block of space-time, so region A from 10:30 to 11, think of that as a cluster. And then I have a bunch of these clusters throughout my day. So if it's every 30 minutes and I have 3 regions, then in a day you have 48 times 3. So what is that? 144. Something like that. You have 144 clusters. And you flip a coin for each of those clusters, and then you assign that cluster to treatment or control. And so it's the exact same idea as before, but now you're just using time as another dimension. And then, and so what's the hope? The hope is that different units of space-time don't interfere with each other, right? So that this control unit at 10:30 to 11 doesn't interfere with this treatment unit at 11 to 11:30. And as long as you have this hope, so for now, because I want to get to your question. So for now, let's assume that this is true. Let's assume that we don't have interference either between regions or between time, right? So each of these clusters actually doesn't interfere with each other. Then what's the benefit of this method? The benefit is that we just dramatically increased our sample size, right? We just went from 3 regions in a day, so a sample size of 3, to if my math is correct, 144 regions in a day. Or 144 clusters in a day. And so sort of based on, what the question was is, like, this is not real, like, this is still kind of susceptible to like random events happening, right? So like this is so susceptible to like in region B, some concert let out at 10:45, and like that completely messed up the marketplace for a little bit. And so it's still susceptible to that. But the idea now is that you just have a lot, like, and so that's just like variance in your experiment is like the real world happens. But now you have a lot more clusters. And so your sample size is a lot bigger. And so events like that don't really, like, if events like that are only affecting one cluster, one unit, one region of space-time. Sorry, I'm keep mixing my words. Not one region, because I'm using regions as space. It's like one unit of space-time. Then it doesn't matter, right? Because I have hundreds of these units throughout my day. And so this is just a trick that if this is true, if the hope is true that different units of space-time don't interfere with each other, then I just dramatically increased the number of units in my experiment without much cost. Any questions about this? Okay, and then you just analyze, and if this is true, if different units don't interfere with each other, then just analyze exactly like you would do a simple A/B test or a simple graph cluster randomization test. And sort of maybe unlike, so like with, so I would say here, like maybe like at a high level, unlike like graph cluster randomization on social networks, is like you're actually often that this assumption is not true. Like often different units of space-time do interfere with each other because, for example, so take that ride-hailing example that I just said, is if I assign, so suppose this is on the order of 30 minutes. Then suppose I launch an algorithm that during treatment makes things free. Every ride is free. And then during control, every time is its regular thing. Then sort of there's two effects that could happen. It's like maybe if writers realize this, then sort of in the treatment periods, they're going to book. And that trades off from the same writer potentially booking 20 minutes from now, right? So you do have substitutability across time. And then in space, for similar reasons, is that if all drivers start their trips during a treatment period, then trips take on the order of whatever, 20 minutes. By the time you pick up, you drop off, you get a new ride, and so on, 20, 30 minutes. Then they're going to be busy into the next control period and not be able to drive. And so often you do end up for these fast switchbacks, depending on what you're trying to test, you actually do end up having interference. But it turns out that a lot of this interference that happens, sort of the idea is that what it's happening through, right? So in this driver example, that all the interference is acting through the number of drivers available, right? That's in some sense the sufficient statistic for the interference. And so in the analysis, I could potentially control for the number of drivers available at the start of the period. And more generally, I think there's a lot of interesting work happening right now on how to design these switchbacks better. So for example, sort of what I taught so far is you just flip a coin for each unit. But it turns out you can actually be fancier with the design and actually take into account this interference in the design. If you assume that all the interference is happening based on the number of drivers currently available, then you can actually decide whether something is in treatment or control based on that number. Happy to send resources down the line. Any other questions here? Okay. So I think that's maybe the summary for, or sort of maybe that's it for new experimental designs. And so any questions on experimental designs before, I'll do a summary just now, and then maybe I'll take questions then. Or questions on switchbacks, and then I'll do the summary. Okay, yeah, so let me do the summary first, and then is your same thing? Okay, any questions on switchbacks? Okay. So we talked about several different designs, classic individual level A/B testing, graph cluster, or more generally spatial randomization, where each unit is either always in control or always in treatment. And then switchbacks, which you're now randomizing over time, the same like listing of the same driver, the same region of space is now sometimes in control, sometimes in in treatment. And sort of there's like two broad lessons that I want to sort of extract from this. I mentioned some of these at the beginning of the class, but I think it's worth emphasizing. The first one, and I'll say this in different words now, is this bias variance trade-off, which if you have smaller clusters, units, and so you can think about these, now you can think about these units as either space-time units or just space units or time units. So if you have smaller units, then they're more likely to interfere with each other, and so you tend to have more bias. And if you have bigger units, bigger clusters, then there tends to be fewer units or clusters, and then you tend to have more variance. And so this is from another one of those Lyft blog posts where they sort of think about what their randomization unit is, and here they just have a silly what's more bias and more variance. But in practice, you would really want to be thinking about which of these randomization units to do, right? So they can randomize at the individual user session. So a user session is someone opens the app and sees something. You can randomize at the user level where now if I open the app twice in a week, I'm in the same unit, and then so on, right? You could go down to even the city level randomization. And as you go down here, you end up getting bigger and bigger clusters that are less likely to interfere, but are more likely, then you just have fewer clusters. And in practice, you really want to be thinking about which, what is the right unit for your experiment. That's probably the biggest decision you need to make in designing a good experiment. And maybe just to emphasize what each means, so what does variance mean here? Variance means if I run the same experiment many times, do I get a different answer each time, right? Or am I getting the same answer from the experiment, right? So are my experimental results really depending on this random noise, like this concert happened to let out during my experiment or something? And what bias here means is if I run multiple experiments, I get the same wrong answer each time. And and this is similar or exactly the same to the bias variance trade-off y'all should be learning in applied machine learning. And sort of the thing the summary here is the same as well. It's at the end of the day, you're only going to be running the experiment once. And so the bias and variance each contribute to your overall error for the experiment. And you want to be, and you're never going to eliminate either. You're never going to completely eliminate variance. You're probably never going to completely eliminate bias. And so what you want to be in a place is pick the randomization unit such that you balance out sort of these things such that on average, sort of to minimize your overall error if you just run the experiment once. And you can make these decisions through something like simulation and evaluating different techniques in simulation to seeing in general which has the best trade-off. And I think this blog post, one of the Lyft blog posts I linked on the website talks about sort of doing exactly that. Was that a question? Okay. Yeah.
I'm having trouble understanding like smaller clusters, like not the basically smaller clusters. I would imagine smaller clusters.
So if you have smaller clusters, then you have more clusters, right? So like think about an experiment where you have 1,000 individuals versus 100 individuals. The one with 1,000 individuals has less variance. And so here, think about clusters as individuals, where if you have 100 clusters versus 1,000 clusters, then the 1,000 clusters will have less variance. So each cluster, so you're right, and this is like some like slightly tricky thing that I wanted to sweep under the rug, is that you're kind of right, is that in each like the value of each cluster might be more variance, but the value across sort of the variance across clusters is smaller because you have more clusters. And so and that's the variance that you tend to care about. Right, so just think of it as, like, don't think of it as clusters changing size and just like think of it as 100 clusters versus 1,000 clusters. You would rather have 1,000 clusters for variance.
Like the multiple experiments across the unit, not like multiple separate experiments on the set of units.
I don't understand the distinction in the question.
Like if you have 1,000 users, right, and you run 2 experiments on those 1,000 users,
Yeah.
then there could be a lot of variance because
Yeah.
those users do this.
So when I say run multiple experiments, like you like literally can never do that, right? You never, like, you literally can't like take the same exact set of conditions and then run 2 experiments, right, with different assignments of treatment and control. And this goes back to the question on like, how do you evaluate that an experiment is good, right? You can't literally run this multiple experiments on the same set of units, right? Just like you can't run you can't treatment and control the same unit. You can't, at the same time, you can't run multiple experiments on the same unit. And so there's like, if you run multiple experiments thing is like a hypothetical that can't happen. And so the way you evaluate this is either in simulation. So in simulation, you can do this all the time. Or you can do like a meta experiment where you're evaluating your experimental techniques. And then you can use these experimental techniques to evaluate like the experimental techniques themselves.
Imagine like big companies like Uber and so forth, they're probably interested in running as many experiments as possible in this given period of time, right? And I know earlier you said like try not to always experiment with other experiments, but is there like theory or practice to do that, to run multiple experiments at once?
Yeah, so I'm going to talk about that next week. Yeah, so next week, I think half of the first lecture, or maybe all of it, depending on time, is going to be like on experimentation. So like, how do you sort of, do things like that, like sort of experimentation culture. Okay, any other questions on the bias variance trade-off? Okay, and then the second one, sort of the second general lesson that I want to do is there's 2 parts of running a good experiment. Is getting the design right and getting the analysis, given the design, actually calculating global treatment well. And so what does design mean? Design is who gets assigned the treatment, who gets assigned the control, and does that change over time and things like that? And how do you assign that? And the analysis is, given the assignments and given like my objective function, how do I given the metrics, how do I actually calculate the global treatment effect, right? So like getting the final answer for the effect of the treatment compared to the effect of the control. And in this entire unit, this module, we've mostly focused on good design, right? Like, there's some analysis in the homework, you do some analysis and like you run a z-test, and I'm not teaching that. And the reason for that, I think, is I mean, yes, if we had an entire course on this, I would do analysis as well. But I think at the level that sort of it's most important to get the design right. So if you do a good design, the analysis should be mostly simple, right? So if you, this has been shown, I think, throughout what I said, is that if you do this design correctly such that there's no interference, you can analyze it exactly like you would a simple A/B test, right? And so the analysis is like fairly simple. But if you do a bad design, like there's no amount of fancy statistics that's going to save you. Like if there's a bad design and there's interference, there's like, and you know, it's interference in a way you can't observe, then it's like unmeasured confounding in the first part of the course, right? In the polling module, right? There's like nothing you can correct for. There's like nothing you can do to correct for unmeasured confounding. The best you can do is to like quantify how bad you are. And so, like when y'all are running experiments, you know, especially in like smaller companies that might not have like this like culture of running experiments done, is sort of you need to be spending the majority of your time on thinking about what's the right design for your setting. And then once you have the design right, then and the design, like, you know, not just thinks about interference, but also thinks about some of these questions I'm going to talk about next time of like, you know, trading off multiple experiments and like how expensive each experiment is and so on. And like, so yeah, so when you're, you know, thinking of running experiments at a new place at a smaller company or, smaller nonprofit or whatever organization you're in, you need to be spending the bulk of your time thinking about the design. And then when you're like a consumer, so suppose you're a product manager and you're like a consumer of experimental results, most mistakes are going to happen at the design phase, right? Is like when someone, like a data scientist, when you're presenting an experiment to someone or someone's presenting an experiment to you, the really sort of like often what I do is like, you know, I just trust that they got the statistics right. And the question is like, did they get the design right? And it's often like, it's funny because in a presentation, it's often easier to think through, did they get the design right? As opposed to like thinking through the math and like their code of the actual statistics. And that's often where the mistakes happen anyway. And so when evaluating an experiment that someone else has run, you should probably be focused on like, okay, did the experiment they run even hope to capture what they wanted to capture, right? And so like if they did a simple A/B test on a social network, then there's like no hope of capturing global control, global treatment. I mean, unless they did the like sort of the fancy analysis, which they probably didn't do. And even if they did the fancy analysis, their like results would be noisy and confounded and so on. Okay. Any sort of questions on design of experiments? Did I answer the questions y'all had? Okay. Okay, so in just a minute or two, let me just finish this summary. So even with all of this, these experimental techniques are not workable sometimes. So like sometimes you just like can't hope to run an experiment of the kind that I said. And so what are these settings? Suppose your product is public facing, right? So like you're announcing like commission changes for like how much the drivers are earning per trip or something. And or just something that requires a big amount of like, so like Airbnb had this entire push for like new picture, like sort of getting like better pictures of their homes on the website, right? So like that requires a lot of effort to like, you know, have someone take good pictures and upload them, get like a camera team in and blah, blah, blah. And so like, suppose the product is public facing, it's really hard to roll it back, right? It's really hard to run like a switchback when you're like, okay, now you're getting paid this much, now you're getting paid that much. Oh, right, like it's like switch back and forth. If the interference is really like network wide or city wide, then like it's it's really hard to like, and so this makes the first thing makes time experimentation hard. The second thing makes spatial randomization hard is that if like you truly have interference across a big chunk of your network. And suppose also your change is sensitive, right? So like you're doing some major change to the platform that some people might be unhappy about, or a lot of people might be happy about, but whatever it is, it's a big sensitive major change, and you can't launch in every city at once, right? You want to test it out in one city and then like expand out through your, like if that goes well, you work out the bugs and then you expand to every city. Then, or it takes a long time for the effect to occur, right? Like the effect is on the number of subscribers to your sort of your product, and subscriptions happen like every month, right? So it might take a long time for the effect to occur. And so if like these things are true, it like becomes really, really hard to run any of the experiments that I just said. And so next time we're going to talk about I'll start out class with like the one analysis technique I'm really going to cover at a high level at least, which is exactly sort of the intuition from your question, which you try to build a machine learning model to understand what would have happened. So you launch in one city, right? So I make the change in the entire city, and then I try to have a machine learning model to understand what would have happened in this city if I did not launch. And you train that machine learning model based on what's happening in other cities, where you truly didn't launch. And then your estimate of your global treatment effect is the difference between what actually happened in that city with treatment and your best estimate for what have happened in control. Okay. So I'll just end with, put the announcements up. And I think that's all I had for today. Happy to take questions offline.